Okay, let's start off on a new subject, air navigation. It's a very important subject. We will be studying this subject almost throughout, and the flying is all about navigating from A to B. It's a very important subject, and there's one whole lot of topics to be covered. We will go step by step and cover the subjects. What is air navigation all about? It's flying from place A to B in the most accurate manner. And let's go a little bit back into the history. Uh, in the earlier days, the traffic uh, was not that heavy, so the challenges were not, also not that critical in air navigation purposes. But with the increase in traffic and with the increase in air density, uh, one has to be very, very accurate in all aspects of air navigation. To that extent, it becomes very critical. So let's go over what has been the challenges, or what were or are the challenges, and then how we are going about tackling these. Okay, firstly, representing the Earth's spherical surface to flat surface itself is it's a study by itself. That's what we are going to study in our chapter of charts and maps, different representations, and what are the accuracies, and what are the current systems thereof. Next is position fixing. That means fixing the position of your current position absolutely accurately. That means if you say I'm in this position, it has to be as accurate as possible. And throughout your flight, during your route flying and etc. And of course, while landing, sometimes you must appreciate we are nowadays doing Cat 3 landings without visual references. So if your system is able to be able to bring you to the accuracy of up to plus minus 2 meters, and that's what is required. Otherwise, we are not progressed anywhere. So we have reached, and so that's what we are going to study. Next challenge which has been met, and then nowadays we have sophisticated systems, is the measuring of direction, or directing the aircraft in a particular pre-selected direction. That is, what are the things which are affecting that? The Earth's shape, uh, the aircraft system's accuracy, and its errors, etc. And next is the speed of the aircraft. The technology of measuring of speed. Earlier we were measuring speed with the pressure instruments, and now we have inertial reference systems from where the speed is derived. So we are going to learn about all this, and the Earth's shape, and aircraft itself is rotating. I'm sorry, the Earth itself is rotating. The aircraft is moving in a direction, uh, and aircraft measuring instruments have its own errors, etc. And last but not the least, there is weather phenomena, winds, which keep pushing you out of your track and giving you drift and errors in your navigation. So we are going to learn about these things one by one in different lessons. Okay, in this lesson, we are going to learn about a very important aspect of uh, measuring the direction and directing the aircraft in a particular direction. So, first is let me talk about Earth's magnetism. In my earlier lesson in Newton's laws of motion, or general laws of motion, I had introduced that every mass in the universe exhibits this magnetic properties, and of course Earth also has exhibits has its own magnetism. So we are going to learn about this Earth's magnetism in a more elaborate manner, because the aircraft magnetic compass uses the Earth's magnetism partially to fix and measure and direct the aircraft in particular direction. Now, we learned in our earlier two lessons in the form of the Earth that Earth's rotation axis, that is, it is tilted approximately about 23.5 degrees. Is it not? So, which is what gave rise to different seasons, etc., etc. Now, while the axis of the Earth, that is the true rotation, or that's what we are going to fix it as true north. That means the axis around which the Earth is rotating, the poles, is, we will fix it as true north. Eventually, all directions have to be referred or brought down to this true north for accurate measurements. However, let's get on to the subject of magnetic properties. As I told you, uh, all the measure, there, unfortunately, there is no way that we can measure any direction with respect to the true north per se. So we have to make use of the magnetic property of the Earth and some other natural magnet to measure, or any other means whereby the magnetic flux can be detected to uh, measure the direction. So here we are going to make use of something called the magnetic north, and because of its properties, mass distribution, and so many other factors, the magnetic north doesn't coincide with the true north. It is in a position which is shifted away from the true north. Now, as I have shown in this figure, I have shown the magnetic flux lines which is pointing towards the magnetic north. And once again, this magnetic north itself is not a fixed point. Or let's see what are the characteristics of magnetic north. The magnetic north position rotates around the true and or the geographic north every 960 years. So it's a continuously changing position. That's the point which I want to reiterate. The next point which I want to say is the magnetic north position and the magnetic south positions are not exactly diametrically opposite. That's another big challenge. Unlike the geographic north, true north and true south will be exactly diametrically opposite because of, by virtue of the rotation of the Earth around that particular axis. However, the magnetic north itself does not coincide in the north and the south. That is, we must understand. Thirdly, the magnetic north position is approximately about 900 nautical miles away from the true north. So it's not a fixed point, it keeps changing. So we have to keep measuring it. We have to keep recharting all our maps and charts and all our navigation systems. We have to keep reworking. That's the point which we need to understand. Okay, now that we defined the magnetic north, how will a natural magnet behave? When you suspend a natural magnet in a free space over the Earth's surface, the magnetic south of the magnet, the south pole of the magnet will be pointing towards the magnetic north of the Earth, and vice versa. And it may find a mean position, because it may not be exact, because the north and south are not exactly coinciding. So that's how we are going to measure. Now, I want to introduce a new term called variation. Variation is the angular difference between the true north and the magnetic north. And of course, there are going to be, it is going to be measured in degrees and annotated east or west depending on the position of the magnetic north. That means if the magnetic north were to lie east of true north, then it will be called variation east, 2 degrees east, or west, vice versa, according. So that is what is variation. Now this is again, it's not constant. It has to be revised periodically. So that's we will learn later. So so that is we call variation. Okay, now that we learnt about variation, let me introduce you to another terminology called the isogonal line. What is an isogonal line? A line joining places having equal variation. So as I told you, it's not a straight line, it's a curved line, it's not a fixed line. It has to be periodically be revised. And here in this diagram, I have shown a blue dotted line which represents isogonal line of 3 degree west. Also, I want you to notice the arrow notation which I have used, which are standard for representation. May not be the color, but definitely the notation, arrow notation is standard. As you can see, the true north has been represented on a line with a diamond, and that's black in color in this picture, and another line in brown color with a triangle edge is representing the magnetic line. And also notice, because the magnetic line, magnetic north, lies to the west of true north, this isogonal represents 3 degrees west. As I told you, there are no simple ways to measure the true north on standalone basis. Of course, the inertial reference systems things are different, but we have to use a magnetic compass or any of the magnetic system which can measure the magnetic flux and compare with the magnetic north. So that is what the compass, aircraft compass, will measure. That means the aircraft compass is going to measure a north with respect to using the magnetic flux. But of course, there are going to be errors and there are directional reference. Even though it tries to measure, uses the magnetic flux of the earth, it doesn't exactly coincide because of several inherent errors. Now, the north which is pointed by the compass is going to be different, little bit different or away from that of the magnetic north. So that's we need to understand. So now we have been introduced to 3 different direction references. One is the true north, the next one is the magnetic north, and the compass north. Just have a look at the diagram and then we will discuss further. Also, I want you to notice the notation which has been used for the compass north, a line and a dot or a circle or a sphere. That's what represents a compass north. Okay, now as I told you, this doesn't exactly coincide with the magnetic north. There has to be an angular difference. That is what we will call deviation. The earlier one we called it variation. Now we will call this deviation. What is deviation? The angular difference between the magnetic north and the compass north is called deviation. It's also measured in degrees and it is annotated east or west depending on the position of the compass north with respect to the magnetic north. That we have been introduced to 3 different norths. Now we are going to measure our direction in the aircraft in compass. Now it has to be transferred onto the true north, and from the maps and charts we will know what is the variation. Therefore, we have to do some mathematics to convert this compass north to true north. So that's what here I have tried to explain. So we have compass north, magnetic north, and the true north, and we defined deviation and variation. Now I will give you some thumb rules so that life becomes very simple. The thumb rule is in the wordings as shown here. Deviation east, compass least. Deviation west, compass best. Variation east, magnetic least. Variation west, magnetic best. That means if deviation were to be annotated east, the compass figure will be less than that of the magnetic figure. That means if magnetic north were to read 355, and if deviation was 2 degree east, that is compass is least, so we subtract from 355, so the compass will be 353. That's what we mean by this whole thumb rule. So this is going to be very important. It's best to memorize it and learn to use it practically. Now, as usual, some numerical example to clear out our concepts. The numerical goes something like this. The true heading is 145 degrees. Variation is 3 degrees west. What is the magnetic heading? Variation. Now we learned the thumb rule. Variation west, magnetic best. Therefore, we will add this. So true heading 145 plus variation 3 degrees is equal to 148. Therefore, magnetic heading is 148 degrees. Now the same numerical I tried to show you in graphical form so that it will be very clear. Firstly, the magnetic north has been shown, the aircraft direction has been shown, and the aircraft true direction measures 145 degrees as shown in the picture. Now let's draw the magnetic north. Now since it lies towards the west, so let's draw the magnetic north to 3 degrees to the west. So which is what I have drawn. Now if you are to measure the aircraft direction from the magnetic north, obviously it is very clear from this picture that it will be more than 145 by 3. That is, magnetic heading would measure 148 degrees. So both numerically and graphically it should be very clear to us as to how it makes sense. Okay, another numerical example. Compass heading is 225, variation is 5 degree east, deviation is 6 degree east. What is the true heading? This is a very practical example. Of course, practically there are very few places where you will come across variation 5 degrees and deviation also 6 degrees. This is just to exaggerate and make the thing very clear. So true heading is 2 to 5, deviation east, compass least. So magnetic heading is equal to compass heading 2 to 5 plus 6 degrees, that is 2, 3, 1 degrees. That means compass is less. So magnetic had to be more. So that's why it has 2, 3, 1. Now variation is magnetic least. Therefore true heading is equal to magnetic 231 plus 5 degrees 6 degrees. Therefore, for this numerical, the true heading of the aircraft will work out to 236 degrees. Okay, once again, the same numerical I try to represent in the form of a graph with the true north and magnetic north. As you can see, everything is lying towards the west, so everything else is measuring as shown in the figure. I have not elaborated too much, but suffice to say that graphically as well, you will arrive at a true heading of 236 degrees. Okay, now we are on the subject of Earth's magnetism. I want to introduce you to another important term and phenomena called the magnetic dip. The magnetic flux lines of the Earth do not exactly run parallel to the Earth's surface. They are, of course, curved, and a freely suspended magnet, as I have shown in this figure, I have tried to represent the Earth's surface and a freely suspended magnet. And if you were to suspend, it is not going to remain absolutely parallel to the Earth's surface. It is going to have a dip, depending, of course, on it, the position of the magnet itself. It is going to dip and just point towards the Earth's magnetic north position. So this angular difference between the horizontal, absolute horizontal, and the plane in which the magnet aligns itself to point to magnetic north is called the magnetic dip. We learned that the magnet dips. Of course, absolute center of the Earth, some places will have zero dip. So this line is called the agonic line. That means all uh, a line joining all places of zero magnetic dip is called agonic line, and it's also called the magnetic equator. Again, it's not a straight curved line. It's not a straight line like that of the equator, but it's a curved line. And of course, it depends on the field strength, position. Zero agonic line is just one line which will be representing any other hemisphere. It's not going to be zero. I'm sure you appreciate that, because the fields are not going to be equal either way. We need to be very careful about this Earth's magnetic flux and its measurement. Sometimes you have this magnetic storms. These are temporary disturbance of Earth's magnetosphere caused by solar wind shock waves. The March 1999 episode, which caused the collapse of the hydro power unit of Quebec in US, is a very good example. The 6 million people, I understand, were left out without power for almost 9 hours. So sometimes it could get as critical as that. What's the significance of these magnetic storms for an aviator? We use GPS extensively in our aircraft for measuring position fixing, directions, etc. So these GPS receivers continue to operate in the presence of some confusing signals. That means even when magnetic storms are predicted and measured or sensed, we are able to distinguish, and they continue to operate in the presence of confusing signals. And we have heard that thing called RAIM, that is receiver autonomous integrity monitoring. But however, RAIM is predicted on the assumption that majority of the GPS constellation is operating properly. So it will assume that 2-3 of them are correct and one of them is wrong, and then it will cater for it. However, if all the satellites were to give error, then it will get confused and it's going to be complex, or it's not going to give correct position. So that's what here I have tried to explain. It is predicted on the assumption that majority of the GPS constellation is operating properly, and so it is much less useful when the entire constellation is perturbed by global influences such as geomagnetic storms, etc. Of course, these are going to be predicted, and then as aviators, we are going to be sufficiently be well warned, I presume. Okay, I hope you found this lesson interesting. We are going to be presenting more and more lessons, and it's going to get more and more complicated as we go. This particular subject is interesting and it gets complicated. Anyway, please feel free to offer your comments, and please follow my YouTube channel and my website for more lessons. And your critical comments will enable us to present better quality lessons. Thank you all for watching this lesson patiently.